Okay, in this video we are going to look at force on a current carrying conductor in a magnetic field. Because a current produces magnetic field, so if you place a current carrying conductor in a magnetic field, in an external magnetic field, there are now two magnetic fields. One is the original external magnetic field, and another is the magnetic field created by this current carrying conductor. And because they interact, the current carrying conductor would experience a force. So first let's find out the direction of force. Let's first find this out. So direction of the force is, you need to use what we call a right hand palm rule. You need to use right hand palm rule, which says that you extend your hand, you open your palm up with the thumb right angle to your fingers. So these are your fingers, just bear with me, and that's your thumb. Yeah, so these fingers is stretched, you opened your palm, and this is your thumb, and these are your fingers. And the whole idea is that this thumb gives you, and then you need to reorient your hand in such a manner that the thumb is in the direction of current. The thumb is stretching in the direction of the current, and the fingers are stretching in the direction of magnetic field. Then the force will be perpendicular to the palm. As simple as that. So I can show you a better diagram. You should be able to see that this is how you do it. So this current and magnetic field, so current and magnetic field, they have to be at right angle, and then the force will be perpendicular to this. So it's a three-dimensional figure now. In this particular case, the force will be out of phase. If this is a current and this is a magnetic field, force will be out of phase. So we could show with a dot. We could show the force with a dot. That's your force coming out of the page. Yeah, and this rule, this is known as right hand palm rule. Let's try some practice on this. So let's look at this thing. This is my magnetic field, and that's my current. What will be this is my scenario number A. Pause your video here for a moment and tell me what would be the direction of force on this conductor here. Okay, if you have used the right hand palm rule, you would see that your just stretch your hands, stretch your palm in this direction, and it will be out of the page. Yep. Take a moment again. If you want to pause the window and take a moment again, you can see why it is out of page. Okay, let's try this figure now. So this is my B, magnetic field, and this is my current. Take a moment and try to find out what would be the direction of force. it is into the page. Yeah, just you need to stretch your hand in such a manner that your thumb is pointing in the direction of I, and fingers are stretching in the direction of magnetic field. Then the palm, the perpendicular to the palm, is gives you the direction of the force on that conductor. Okay, let's try this time. I will use a magnetic field which is perpendicular to the page, coming out of the page here. So this magnetic field, this is my magnetic field, it's coming out of the page, and I got this is my current here. So again, I want you to take a moment and think about it and tell me what's the direction of force here. Yeah, so force will be upward on the page. Oh, sorry, hang on, I made a mistake there. So this is the current is in this direction, magnetic field is out of the page, so it will be downward on the page. Downward on the page means that will be the direction of the magnetic field. I can show it here. Instead of showing it here, I'll show it. That's the direction of force. Okay, we'll just look at one more example. So this is my current this time, and this is current carrying conductor, and that is my magnetic field. So what would be the direction of force in this case? The force will be towards the left of the page. So towards the left. So I could show it like this. Let us look at two more examples, just a little bit more of practice on this. So my case E is like this, that magnetic field is indicated by crosses here. That's my magnetic field, and that is my current. I want you to find what's the direction of magnetic field here. Again, you can pause the video and give yourself a go. This force will be to the right. Yes, so that will be to the right, and this is your current I. That's the current I. That's your F. And the last example in this series is that this time this is your current, this is your conductor perpendicular to the plane going into the page, and your magnetic field is this. So the force here would be, take a moment again, force will be in this direction, upward on the page. So we have seen the direction of the force on a conductor which is carrying current and which is lying in the magnetic field. But what about the value? The value of the force is given by this formula: F is equals to BIL sine theta, and different values, like the meanings of letters is like this. B is the intensity of magnetic field, and it has to be in Teslas. Then I is current passing through the through the conductor, and it has to be in amperes. L is the length of conductor lying in the magnetic field, and theta is the angle between B and I. I think it will be more clear if I draw the diagram here. So suppose this is my magnetic field and that is my current I. So this angle is theta, the angle which is the conductor makes with the magnetic field. Now from this equation, F is equals to mil sine theta, we can see that F is equals to 0 when theta is equals to 0 degree or theta is equals to 180 degrees. So in these two cases the force is equal to 0. This is my B and that is my current. They are in the same direction. Here angle equal to 0, so F equal to 0. And other one is, this is B and this is my conductor carrying current in the opposite direction. This is my I. Again here theta is equals to 180 degrees and the force will be equal to 0. So from this discussion it would be clear that if the current is parallel, I mean we talked about it that the current is parallel or anti-parallel, the force equal to 0, it would be clear now that the force comes into existence only when current and magnetic field are perpendicular to each other. Yeah, and this thing is important. So let's go back to this diagram here. How would you find the direction of the force here? Because normally when we use the right hand palm rule, we have our thumb extending in the direction of the current and B extending in the direction of magnet and fingers extending in the direction of magnetic field B. So basically we are assuming that they are at 90 degree because your thumb extended and fingers extended, they are at right angle to each other. But in this case here, if you want to use the right hand palm rule, you will see that your thumb is not stretching completely. Combining these two things into, I mean, looking at this discussion here and looking at this, we can see that only that part of the current would cause the force which is perpendicular to B. So look at this current here. This current is I here. It can be broken down into two components. One component is in the direction of B and other is in the direction of other one is perpendicular to B. And as we discussed, the parallel component, the component of current which is parallel to B, will cause no force, and force will only be because of this component, right? So in such situation, how do you find the direction of the force? What you do is you draw. So what you do is you draw the component of current perpendicular to B. So you draw current component perpendicular to B, and keeping in mind that this is the only component which produces the force, which is responsible for the force, you now use right hand palm rule with the fingers extending in the direction of magnetic field and thumb extending in the direction of this component, this vertical component, but this component here. So write this here. Right hand palm rule. What would you use here? Fingers. I should say extended fingers. And that one is the thumb. And now you use the right hand palm rule to find the force.